right, welcome back to system software. So, some housekeeping items to get out of the way real quick. So you should have lab accounts activated tomorrow. Also, with your lab accounts, there's going to be an optional tool to help you. So one of the previous students has developed some tool to help you prioritize what assignments you should complete and what you should study for and all that. So you'll get details posted about that. If you would like to help out, that would be greatly appreciated. So today's lecture is kind of a fun lecture. You don't have lab set up or anything. So sit back, relax, and enjoy the ride. I will tell you the few minor things you actually need to take away from this lecture. But this is another setup lecture, so don't be too worried if it's kind of confusing. So why is it confusing? Because, well, this is hello world. So this is hello world if you write out each individual byte in hex and you try to execute it. So let us make sure that I wasn't lying to you and that this, in fact, is hello world. So if I look at my directory here, let's see, I have a file called hello world Linux ARch64. We'll get into what that means in a second. And here is the file size. It is only 168 bytes. And if I execute it, prints hello world. Amazing, right? So we're going to dive into the details of how this works, and it will set up kind of where this course is aimed at and what we need to take away and what we'll learn from this course. And we'll also figure out why JavaScript is terrible. All right, great. So I've showed you this actually is hello world, so let's get into it. So first aside that you don't need to know, that may come up. So there's three major ISAs or instruction set architectures in use today. It stands for, like I just said, instruction set architecture. It's the machine code or the magical numbers the CPU understands to tell it that it needs to add two registers together and things like that. You probably have hopefully done a little bit of assembly, but it's the lowest level. It's what your CPU actually understands. Three main ones today is x86 64-bit, so that's like any desktop processor you have, any laptop you have that's not an Apple one. Then you have ARch64, aka ARM64, that's like any phone, tablet, or Apple laptops will be using that. So I had to execute specifically that because, well, I have an Apple laptop, so it's ARM. The next one that might come up a little bit in this course that we will read, but don't worry, you don't have to look it up or anything, is RISC-V. Might be called RV64GC. It's an open source implementation of an instruction set architecture, so you are allowed to implement it yourself, possibly in future courses, without having to pay ARM a licensing fee that costs millions and millions of dollars. So we'll touch on them a bit in this course, but not important. Just something you should know because it's going to be important today, but again, not to understand. So the next abstraction we have in this course is something called a file descriptor. So we already argued that our processes are independent. They have their own independent memory, and if they're independent, well, they need to be able to transfer bytes to one another somehow. Otherwise, you wouldn't be able to see their output or give them input or anything like that. So something that is important to know the acronym for is something called IPC, or inter-process communication. Don't worry, we'll get to it again later in this course, so it will come up again, but if you want to note it now, you can. And all IPC is transferring data between two processes. So a file descriptor is just a resource that users can read or write bytes from. So it's actually identified by an index, and that is stored in a process, and that is how your process can actually communicate with, you know, your hard drive and your storage and all that fun stuff. It could also represent different things from a file, even though it's called a file descriptor. It could represent your terminal or things of that nature. And we'll get into other things it can mean as we progress through the course. So there are ways to ask your operating system to do something, and they are special in that they are not C functions or anything like that. They are, in fact, called system calls. And that is how you make a request for the operating system. You probably have never done this before because this is what the C standard library does for you. But in this course, we'll be actually understanding what the system calls are and what they do, and that's kind of where this course is aimed. So there's two system calls we need to use if we were to have the bare minimum hello world program. There's a system call called write that takes 3 arguments. The first one is a file descriptor, so it's just a number, and then that should represent a file or a terminal or something like that. And that is where to write bytes to. And then because it's C, it uses pointers, so there's a const void star pointer called buff. If you haven't seen a void star before in C, that just means it's a pointer and it doesn't really care what the data type is. It's C's way of saying just a pointer, don't care. And then, so it gets a pointer, and then the third argument is the count or the number of bytes to start reading from to write out starting at that address. So 3 arguments, file descriptor, an address to start at, and then the number of bytes to start writing out from that address. The next system call we need is something called an exit group system call, and it takes a status, and what it does is it ends the current process from running. You might or something like that. And that exit status code is just a number between 0 and 255. By convention, 0 means there are no errors. And again, you don't actually have to know this, but it might come up during the course. All right, so our hypothetical hello world, so by convention, and this is the only way programs work, is that there is some expected file descriptors. It is good to know these numbers. You don't have to write them down right now, but as you go through this course, these will be burned into your mind and you will start just representing the standard file descriptors as just numbers. So you've probably heard of like standard input, standard out, standard error. Well, they're just given magical file descriptor numbers. So whenever we refer to standard input to Unix operating systems, at least, that's just file descriptor 0. If I say standard out, that's file descriptor 1. If I say standard error, that's file descriptor 2. So my most basic hello world program, if I could just magically write a function to start executing, all it would contain is this, a write system call to file descriptor 1. So that represents standard output. And then this is my string to write, so hello world with a new line. And from that C string, I only want to write out 12 bytes. So I want to write out HELLO space world, and then the new line is another byte itself. So after writing out hello world, all it has to do now is an exit group system call, and now that process is done, and this is the bare minimum we need to have a hello world program. So any questions about that one? All right, well, the ride doesn't actually get that much more wild than this. So here's another aside that is probably important to know if you don't know it already. So there is something called an API that you probably all have hopefully heard of before, and then an ABI, which may or may not be new. So an API, to distinguish between the two, it just kind of abstracts the details and describes the arguments of a function, what it returns, and then what it does. So, a function takes 2 integer arguments and multiplies them together or something like that. The opposite side of that is an ABI that specifies the details and specifically describes how to actually do a function call in machine code, like where exactly the argument should be. Should they be on the stack? Where should they be on the stack? What order should they be in? Where does the return value go whenever the function gets called? And if you've done any assembly, you've probably heard of a calling convention. So the caller has to put arguments in a certain way, and then the actual function needs to read them in the same way. If they agree with each other, your code works. If they don't, you will never ever debug it, and you'll be stuck on it for probably a good month. So an ABI is like the actual nitty-gritty details for that architecture. So the same function using the C calling convention, which by default passes arguments using the stack, which is only slightly true. All right, so system calls are not C functions. System calls like have an 8 as the same API as functions, but the way the mechanism to actually call them is a bit different. So with C functions, they're just an address that you can call, and you set up some arguments, and then you jump to an address, and then you jump back, you read the return value, it's somewhere. With system calls, we're actually asking the operating system to do something. So its instructions is not loaded into our memory. It has its own private memory that only it can touch, so you are not allowed to touch it, and that's how operating systems provide some type of security. So you can't just do a function call into your operating system, you have to do a system call. Yep?
I was wondering if there are any privileges that you can activate or system overrides that you can use to access those commands as the user?
So the only thing to do to access special operating system protected things is to make a system call, and that's it. Yeah, so we'll get into that a bit. So knowing the system call ABI is not terribly important, but just in case you want to see the mechanisms, how it works is instead of doing a jump instruction or something like that, it calls a special instruction called SVC, and that generates an interrupt that the kernel can go ahead, that the operating system can go ahead and handle. And it does not use a stack, it passes arguments in registers. So on ARM64, they just generically name registers with just X and then a number. So the convention is that in register X8, you put the system call number there. So the write system call would be associated with some magical number. The exit group system call would be associated with a different number. And then you can have up to 6 arguments that are in registers in this order. So compared to C that uses a stack, what are the limitations of this ABI? Yep.
You can't pass more than 6 arguments, or jump very.
Yeah, I only have 6 arguments, so I can't pass anything more. What about if I also want to pass something that doesn't fit in a register? Then I can't do it either, right? So I'm limited here with C. Since it's stack-based, I can use essentially as many arguments as I want until maybe I stack overflow or something like that, but we'll ignore that. And C arguments can all be of different size. In this case, everything has to be a register or fit exactly in a register. So there's some limitations, but you as a user, you generally don't see this because you don't use system calls directly. So here's finally the last assign. So the C ABI or calling convention for x86 actually does use the stack a bit. So arguments are pushed on the stack from right to left order. Then some registers are callee saved, some are caller saved. And with this, some arguments are actually passed using registers instead of a stack, but it gets into some nitty-gritty details. So if you want to see the details, again, not important. I don't suggest that as reading unless you are a psychopath like me. But you can ignore it. The only important things we need to know, system call uses registers. This uses a stack. So what other advantages does this give us? Well, we already kind of named it. You can have any arguments you want, and they can be different sizes. So the next thing to explain what a program is on Linux, so it uses something called the ELF file format to describe how to actually execute your program. So ELF, again, has nothing to do with me. It is a clever name invented by computer engineers or computer scientists that do not, are not terribly clever. ELF stands for executable and linkable format, and it's the format for both executables and libraries. So they always start with 4 bytes, 7F, and then ELF in ASCII, and again, that is called magic, and that is how a computer knows what a file is, and they just read the first few bytes and then see if they match some hard-coded value, and if they match, well then it just interprets the rest of the file as if it was actually that format. So there's a whole list of file signatures in case you're interested. Again, I don't have terribly interesting hobbies, so I like that stuff. like PDF files start with ampersand PDF and then a tilde, I think it is, or it's a dash. So all of the files are just looks like that. So that is what our bytes, oh, sorry, yep.
So from the previous slide, was that specific to Linux or the ISA?
So for this file format, it's specific to Linux and PlayStation. And BSDs-ish. But macOS has their own, Windows has their own. And PlayStation, Sony was just like, yeah, let's just use this one. Yes, that's true. All right. So our bytes, that's what they represent. They represent ELF file. And to do a too long didn't read of all the bytes, it basically tells the operating system to load that entire executable, all 168 bytes, into memory starting at address 10,000 in hex. So there is a file header that's 64 bytes, and a program header that kind of says where to load something into memory, and that is 56 bytes. So those 128 bytes are just describing what are in the file, and they're not actually doing anything. So like the header will contain things like, what architecture is this for? What operating system is it meant to run on? What byte order is it in? And boring details like that. So the next 36 bytes are just instructions, and we don't need that many instructions. And the next 12 bytes are just for the literal string hello world with a new line. So if we lay out the file such that we have our headers that describe the file and then the instructions would start at address 10,078 in hex because 78 is 120. So the first 120 bytes are just header files. So instructions would start at that address. And then the string that represents the actual data of our program starts at address 10,009C because it is directly after the instructions. So it would start at byte 156. If you want to get into the gory details, there is a program called readelf that will show you all the information about a file, and you can go ahead and look at all the gory details if you want. Again, do not suggest it because it's kind of boring. So this is visually how it gets divided. So the file header has like the endianness, the ISA this program is in, where to actually start executing it if I want to run it. So it has an entry point that's just the address to start executing instructions before. Again, this is what the operating system actually uses. So in C, whenever they told you it begins execution at main, that is not true. It starts executing at whatever address that entry point is, which will probably be the C runtime. Yep.
Does the data actually come after the instructions, despite the fact that that string was, in the middle of the file when we created it, or the middle of the execution?
Yeah. So in this case, I could have put the data in whatever order I wanted, as long as it was consistent.
So is that sort of specified in the header then?
Yeah. So the header says what to load into memory, and then tells it where to start executing from. So part of, so this big blob of stuff just says load this whole thing into memory starting at address 10,000. And this will say what address to start executing from. So if I wanted to, I could shift the instructions to the back and put the data ahead of it, but I just have to start executing at the beginning of the instructions, whatever address I choose.
Are you the one who controls, how the instructions and the data looks like, or
Yes.
does a compiler typically do that?
So this is what the compiler will generate for you. In this case, I wrote it by hand because again, my hobbies are not that interesting. So I decided to lay this out, but your compiler will lay it out however it wants to. But the only rule is that it has to begin with ELF and that the first 64 bytes have to be the header, and it describes the rest of the file. You can do whatever you want. You will never do this, so don't worry about it. So this should be a advertisement as why we use compilers, because otherwise, you're like me. All right, so if we plug in those, so if I take what's in the green there and plug that into an online disassembler, and I actually disassemble it using ARM64, I'll see that my disassembled instructions are something like this. You might use a disassembler if you get into, playing with exploits and all that fun stuff. For this course, thankfully, we don't have to do it. It's only for this lecture. So if you disassemble the instructions, you'll see that it actually follows that system call ABI. So it does a move x8. So x8 is the register where you put the system call number in. In this case, it puts hex 40 or 64. So 64 corresponds to the right system call. And then in the first argument, that's my file descriptor. If I want to output to standard out, that's file descriptor 1. So I move the value 1 into that register. The next argument is the address of the string to start writing out. We argued before that it was 10,009C all the way back here. We said the string data starts at address 10,009C. So because it's ARM64, we have to do it in 2 steps. So we have to load the lower bytes of the register with 9C first, and then this move K essentially just adds it together. So it adds 10,000 to that. So our resulting address in X1 is going to be that 10,009C right here. So after that, the last argument is the number of bytes to actually read from those memory addresses, and it's 12, which is C. Then we do SVC 0. It takes a number argument, but it never gets used, so it's always just 0. So that SVC will initiate the system call. So then my operating system will go ahead, write those bytes out to, in this case, our terminal, and then whenever it is done writing the bytes out, it will return and start executing the next instruction, which would replace the value in X8, so that's a new system call number. Turns out exit group's number is 5E or 94. And then the last thing is the status, and while we just return 0 from main, 0 usually means no errors. So only one argument, we set to 0. And then it does another SVC instruction or initiates a system call, and then our process is done, we're done running. So any quick questions about that? Again, don't really need to know. It's essentially the same thing as we had before. It's essentially the body of that function, but just using the system call ABI and written out just using assembly instructions. All right, all right, so the last part of that is the data for our hello world example. So 12 bytes, hello world, and the new line. So if we ASCII encode it, that's what they are. So weird low-level ASCII tip won't come up for this course, but if you really want to know, bit 5 is 0 if it's uppercase, 1 if it's lowercase, because the values differ by 32. And well, why did they design it that way? Because computers back in the day were dirt slow, and checking a bit is about the fastest thing you can do. That fact of just checking a bit is the fastest thing we can do may come up later in the course as well. So that's every single byte of our 168-byte program, all accounted for, and 120 of those were just header files that we had to explain what the hell we were doing. So let's see how big C is. So I have previously, any guesses as to how big hello world is going to be when I compile it using C? We got a big, what's big? 1 megabyte? 12 kilobytes? All right, let's do over under. Over under, let's go everyone, under 10 kilobytes. Okay, under 10 kilobytes, all right. Anyone over 10 kilobytes? All right, few people don't have any hope in C. The people that had no hope in C are correct. So that is, what is that? 70K. So they tell you C is efficient, right? Well, let's see if it does anything different. Hello world. Mine is what, 168 bytes? What does mine do? What the hell? So C does a lot of stuff. They told you C was efficient. They lied a little bit. Oh, and can you also spot the difference in strings compared from our example to C? So in C, what do strings always end with? A null. Did I have to use a null character? No, because to your operating system, that's just a C thing. Your operating system doesn't care. 0 means nothing to it. 0 means nothing. That write system call has to be super generic and work for anything. If it assumed there was a null terminated byte and that's how, like, where to stop writing data, that means that you could never write a 0 byte out, which would be a very terrible operating system if you could never write a 0. So now we get to use the term kernel finally. So the definition of an operating system is a bit fuzzy because sometimes it includes libraries and other things that we need to, but what is not up for debate is that the kernel is the core part of your operating system, and it has a fairly not surprising definition. So the magic for that, I heard someone say it earlier, that kind of the operating system does some privileged instructions. So on your CPU, there is a specific mode you get to set that tells you what instructions you are allowed to execute. So one of the modes on your CPU is something called kernel mode. And if your CPU is currently switched to that mode, it means you can access more instructions that can actually interact directly with the hardware and actually control the hardware. Otherwise, there's another CPU mode. What you have used currently so far in your career is all your programs run in something called user mode, which has less privileges. It can't change any hardware directly or anything like that. If it tried to execute one of the privileged instructions, you would get an illegal instruction, your program would crash immediately. So the kernel actually runs in kernel mode. Some different architectures also have a different name for this mode. On RISC-V, it's called S mode or supervisor mode, but they mean the exact same thing. So the definition of a kernel is not terribly fun. So the kernel is just software that is running in kernel mode. So for example, if you've ever heard the term the Linux kernel, so Linux by itself is technically not an entire operating system. Linux by itself is just a kernel. So the only way to interact with Linux is by using that system call interface. And aside from that, Linux doesn't operate below that. And Linux only runs in kernel mode with those privileged instructions. In order to have an entire operating system, you need like a C library and things like that that are not included in Linux. For like Mac OS, something like that, they have their own kernel. It has a different name that you've probably never heard of before. It's something called Darwin. Windows has like an NT kernel or something like that. So every operating system will have a kernel. Most of them you probably won't know their name, but technically Linux is a kernel. So like I said, these kernel mode instructions, they're the security measures. So they only allow trusted software to interact directly with hardware, and that trusted software is called the kernel. That gets to control everything, and that's the main part of your operating system. So for example, for security, like the kernel is the only thing that is allowed to manage virtual memory for processes because it is in charge of security. If the kernel has an error in it or something like that, and other processes can start reading each other's memory, then you essentially have no security anymore. Any process can go ahead and read your bank account information or anything like that. So super important that the kernel works properly and is secure, and we'll go over, this course will focus on what the job of the kernel is without having to get into the nitty-gritty details, but this course pretty much operates on that system call interface. We're going to learn how to use it properly. Every program is going to use it eventually, and we're also going to understand what the system calls actually do. So again, here is it graphically. So there might be more CPU modes on your processor. Like for ARM or for RISC-V, they defined 4 different modes. So least privilege is this user mode up here. That's where your applications and libraries run. That's where most of the code you've written this far in your life actually runs. And it is the least privilege. It has no access to hardware or anything like that. The next is the supervisor mode. So that can interact directly with hardware. And that actually manages things like virtual memory. What has more privileges than that is something called a hypervisor mode, which we will not get into until the very end of the course. But in Lab 0, well, as part of this course, you'll be using a virtual machine. So your virtual machine manager is actually running in something called hypervisor mode because it needs to make sure your virtual machines are secure. So it needs to have access to even more hardware instructions than the kernel itself. And then below that, there's machine mode, which if you did assembly before is probably where you were. It has no security whatsoever. It can just access everything. And that's primarily for like bootloaders and firmware stuff we will not touch in this course at all. That will be an embedded course later on. So the system calls are the only way to get between that user mode and kernel mode. And you can think of it, again, like the API of the kernel. So the kind of surprising thing is that's the only way to talk to hardware, essentially. And there's, at the time I did this, there's only 453 functions that you're allowed to use. And that is how every program interacts with the hardware. So surprisingly few functions or system calls, if we want to be accurate, that everything has to use. The nice thing about system calls, so the important thing from this lecture in terms of actually your career later and figuring out what things actually do, for now, you won't really know what the system calls mean aside from 2, but this program is very, very handy. So there's a program called strace. So if we run strace, we can see what system calls our programs actually do. And this leads to a lot of fun. So we can use strace. It will tell us all the system calls any application makes. And because we have this strict user mode, kernel mode, it tells us exactly how it interacts with the kernel. And we can see exactly what it does, no matter what language it's written in or anything like that. So for instance, if I strace this, my Hello World application, and I do this, so this will just throw away the Hello World that it outputs. So it takes file descriptor 1 and throws it to this device called dev null, which just is essentially a black hole. So if I run it, it'll tell me all the system calls I make. So this first system call I did not make. We will get into that later. This is what I actually did. So I did a write system call and then an exit group, and then that was all my process is done. So since we have this tool, we can just see what C does. So we will take this, strace, oops. So we'll probably need to scroll up. So at the end of the day, C did what we expected. Doesn't matter what language it's written in. It did a write system call to file descriptor 1 with hello world, 12 bytes, and then an exit group. But it did some other stuff. So what the hell was it doing? So did this system call, don't know what that is. mmap, we have no idea what the hell that is, but that has to do with virtual memory. See, it did some preload, something or other. No, got an error. Okay, so it just gave up. Oh, something with the cache. Oh, caches are good. We like that. Something we don't know. More virtual memory. Oh, hey, that's interesting. Open, what's that? Oh, it's libc. Oh, well, that makes sense. It has to open libc if it wants to do anything. We can see here that, so open@, will return you a file descriptor number. So file descriptor 4 represents the standard C library. Does a read system call here. We can see that the C standard library starts with something that is already familiar. For some reason, again, don't ask me why, this, when it escapes, the number is an octal. Don't ask me why. This is 7F, but an octal. So it's 7F ELF. So it's an ELF file. Standard C library is an ELF file. That makes sense. Does some more virtual memory stuff. Who knows what the hell it's doing? Some other stuff, don't know what it's doing. Let's see, get random. I don't know. Why does it need a random number for hello world? I have no idea. BRK, so this actually has to do with your heap. So if you say BRK with null, it tells you where the beginning of your heap is. And here it's just reserving some heap storage that turns out I don't need. And then I do my write and then exit group. So cool. Want to try it with Python? So, like I said, this course is relevant no matter what language you write because everything has to go through the kernel. So we can see what Python does. So let's see what Python does. Whoa, wow, that scrolled. But what did it do? So at the end, it did exit group. Well, it had to, because that's the only way to end a process. And up here is my write. So it did some other things before that. It seems also to be weird. So it read the Python file that said print hello world, and then it went back to the beginning and read it again. So I don't know why it did that. So if you want to go fix Python, you can have at it. It clearly has some issue here. But you can see it read that my source file, or it opened my source file here. It looked at my directory. It did some other weird things. It got some errors. It loaded some Python packages. Let's scroll up a bit more. What else? Oh, it seems like it did a lot of stuff. Whoa, what are you doing, Python? Oh, there we go. So when Python started, hey, it kind of did the C stuff. Oh, it uses the math library. Math library is an ELF file. Uses a Z library. Oh, there it goes. So yeah, Python uses a C standard library, so that's cool to know, but did a lot of things. So we can see how much stuff it did. So -2, so it did about 366 system calls for hello world. C did like 34, 33, I think, and we only really need 2. So now we can objectively see how bad JavaScript is. So let's try this again, but with JavaScript. All right, so, oops. All right, any guesses for JavaScript? Is it going to be way worse than Python or way better? Way worse. All right. Better? All right, so it ended with exit group. It should have printed hello world at some point, so write hello world. Does anyone see write hello world on that screen at all? All right, so I will scroll through it quickly, or not quickly, slowly. Tell me when you see write hello world. So that was a write to file descriptor 13, a bunch of zeros. What? Anyone yet?
Is this why Chrome uses so much memory?
Could be. Have we seen it yet? No, we. Oh, there it goes. What the hell does it need to do after Hello World program? It's done. So we could scroll up, see it does a lot of things. So if we see how many lines it actually did, ooh, my laptop's warm now. All right, 1,045 if I minus the 2 lines. So objectively, it's probably at least 3 times worse than Python. All right, so you can go ahead and do that for any program you've ever executed. If I wanted to, you could strace VS Code, you could strace Chrome if you want. It will produce a lot of output. Probably don't do that unless you want things to go slow, but you can figure out what anything does. And if you have to ever reverse engineer something or just figure out what it does, again, don't care what language it's written in, nothing, just strace it. It'll tell you what system calls it makes. And after this course, you will understand a lot of the system calls and then generally what they do. All right, yep?
Does the strace command automatically put it in a TXT file, or is that you?
No, I did that.
Okay.
Yeah. Yeah, so the strace command, you can tell it to output to TXT or a file name if you want. It has a bunch of different options. Yep.
If you strace VS Code when you're running the strace, is it recursive?
You can tell it to follow processes and be recursive, yeah. So you can tell it to just keep on going. But yeah, you can use strace for everything. Strace, at the end of this course, strace will be your friend. You can impress everyone, and then you can objectively say, how bad or worse something is. And so we even saw some weird Python inefficiencies because it read the same thing twice. Well, I didn't even need to know Python or know what it's written in to see that that's probably not a good idea. Any other quick questions? All right, that was a fun whirlwind tour. All right, so just so you have it, I don't really know why I put it on the slide. These system calls are all too long didn't read for finding the C standard library, so it needs to figure out where it is. And then it loads the standard C library into memory. And then it sets up the heap, even though we don't use it. And then it finally does our printing. So at the end of the day, we also saw no matter what language it was written in, because everything to interact with hardware at all or to communicate between processes, it has to go through the kernel. So it has to use a system call so we can see what any program is doing. So we saw the write system call with Python, we saw it with JavaScript, we saw it with C. Doesn't matter. So, oh, yep.
Can you explain the return type? It's a bit far behind, but for the write function, it was an SSIT.
Okay, so I'll just say it. So the write system call has a return value. So if you and actually printf has a return value. Anyone want to tell me what printf returns? How many of you actually knew printf returns something? Oh, yeah, one.
Return if it actually did it?
Nope.
No.
Kind of. Yep.
Is it the number of bytes it printed?
Yeah, the number of bytes it actually printed. And the idea behind that is, hey, you could actually check for errors, because if it printed nothing, well, then that's probably not a good thing. But how many of us have checked for printf? All right, everyone's laughing, so probably no one. So write does the same thing. It just returns the number of bytes actually written out for you to check for errors, because, well, I could have written out, requested 12 bytes, and the kernel could be like, yeah, no, I didn't do that, sorry. And, well, in this case, I wouldn't have caught it because I didn't have any error handling code at all, but I probably couldn't do anything about it anyways, so turns out it doesn't really matter. But write and printf just return the number of bytes read. You've probably never actually used it before. In this course, we'll have to check for errors, so we'll do some write system calls, and you should probably check for errors for those. So you can think of the kernel as a long-running process. So writing kernel code is actually more like writing library code too, because there's no main function. So as part of Lab 0, just to get you familiar with how it looks without actually writing real kernel code, you will write a kernel module yourself, and then the code that you write is actually going to execute in kernel mode. So if you knew what instructions to call, you could actually mess with the hardware, and that's why I have you set up a virtual machine so you do not destroy something. So the kernel lets you load some code into it as it is running. So as soon as you boot up your computer, your kernel's running. So the code you're allowed to insert into it that it executes is called modules, and they load on demand. So I can force it to load. Sometimes they load whenever you plug in like new hardware, like a new USB device or something like that. And again, those are the code you're writing in your kernel module is writing in kernel mode. So if you wanted to, you could just end every single process on the machine if you want. And again, that's why we don't have you actually accessing some real hardware. So this is the only actual important thing in this lecture. So kernels have different architectures. So the different kernel architectures separate what software runs in user mode and has no privilege versus what runs in kernel mode or kernel space and has access to the privileged instructions. So things like virtual memory, process scheduling, so deciding what process should actually execute, and IPC are all in kernel space. And then other things that could be in kernel space are like your file systems, how to actually access the devices. That would be device drivers. So actually, interacting with your storage device and figuring out how that data is stored. So the first architecture is called a monolithic kernel, and that pretty much runs everything it can in kernel mode. And this is what Linux is. So anything that even is remotely has to do with hardware, it's all running in kernel mode. So some people, most researchers think that is very bad because, well, if there's a bug in any one of those components, and then you can start escalating your code and actually start running in kernel mode, then you have access to the entire machine and it has no security anymore. You get to control it. So there is another architecture called microkernel, and the idea behind that is it puts the minimum amount of services in kernel mode and then puts the rest that it can into user space. So things that have to be in kernel space are like basic interprocess communication, so they can actually be separated from each other. Process scheduling, what process one runs which, and then virtual memory. And then in user space, you can put some more advanced IPC up there, device drivers and file systems. So don't worry about memorizing this right now. It will make sense as we go through the course and figure out what each of these do. But knowing the two different architecture styles is good. So there's other types of kernels too, called hybrid, that are kind of between that monolithic and microkernel. So sometimes in Windows, any emulation will be done in user mode. So like old DOS and like old versions of Windows will be done in user mode instead of the kernel. And then on Mac OS, because, well, Apple doesn't want you monkeying around with their kernel, they'll put device drivers and things in user mode so that, hardware, people that are just creating hardware don't get to touch the sacred Mac OS kernel. And then in research, there's things called nanokernels and picokernels that aim to like push more things out of kernel mode. And that's a line of research if you happen to be interested in software research. There's different architectural lines you can draw with different trade-offs. Yep.
Why is it that moving stuff from essentially kernel space to user space makes it more secure? Because wouldn't that mean that more programs can sort of access that kind of stuff?
Well, the idea is that the more stuff I move in user space, that less code is actually in kernel mode. And the less code you have, the less likely it is to have a bug. That's the whole idea behind it. So it kind of depends on code quality. That's why the Linux kernel is so popular because, well, it's monolithic and it's good. So seems to work out. All right, so lessons from the lecture: kernel part of the OS that interacts directly with the hardware. System calls are the interface. Those are the two important things. And then the other ones were not important. File format, not important. Different architectures, slightly important. We'll get to them later. So just remember, pulling for you. We're all in this together.